So now we're going to look at open systems. We'll look at constant property open systems first, and then we'll move on to a general process towards the end. So if we look at an open system, and we know we can have a fluid enter and leave, we could have multiple fluids enter and leave, we could have work being produced, and we could have heat going in. We could have that going in. And to simplify our notation, let's have it be the mass flow rate going in, and we'll use E for energy, and we'll have E2 coming out with the mass flow rate, where E is equal to H plus KE plus PE. So rather than write out H plus KE plus PE all the time, we'll just use E. We know for an open system that the power is equal to minus m dot VDP. And we know that the first law is Q dot plus m dot E1 is equal to W dot plus m dot E2. And so now what we're going to do is apply this law to different systems. And the first system we'll look at is a constant pressure system, which we use for modeling heat exchangers typically. So typically heat exchangers are modeled this way. And let's look at a heat exchanger, and perhaps we'll model a car's radiator. So we have a heat exchanger, and I'm going to have hot water go in. So let's say this is the hot fluid from the car's engine. It goes in, we have 0.2 kilograms per second at 100 degrees C, and perhaps 200 kPa. And it's going to leave at 70 degrees C. We'll then have air. So this is the hot fluid being cooled off. We're going to have the air go in and provide the cooling. So here we have the air, and we'll have the air go in at 300 K, 27 degrees C, and leave at 330 degrees K. So we'll have it leave at 330 degrees K. And now we can find the properties, so we need to find the properties of the water and the air. So let's, with our consistent, this is state 1, state 2, state 3, and state 4. So we're looking at these 4 states, and we'll find the properties of them. So for H1 is equal to H sub F at 100 degrees C, and that's 419.61 kilojoules per kilogram. H2 is equal to H sub F at 70 degrees C, so that's equal to 293.76, same property. And now, so we've looked these up, and we know that for an ideal gas, we can use, for ideal gas, delta H is equal to C sub P delta T. So we have our equation of state for an ideal gas for the change of enthalpy. So now let's look at the heat exchanger. Both substances are at constant pressure. They're separated by tubes. And so now we'll apply this, and let's look first at the control volume for the water. So if I take the control volume for water, and it's going through like this, and we have our control volume be something like that covers it. So in this case, I have the water going in at state 1, leaving in state 2, and there's Q dot is leaving, and it's going into the air. So now let's write the control volume for the water. We wrote the equations that govern this. So I have Q dot plus M dot H1 m dot W is equal to W dot plus m dot W H2. There is no work being done because it's a constant pressure process, and I can solve that Q dot is equal to 0.2 times 293.76 minus 419.61, or I get that Q dot is equal to minus 25.17 kilowatts. So this is the heat that's leaving, and now we look at the control volume from the air perspective, and heat's going into it. So let's look at the control volume for the air perspective. So here I have the air, and again, we have our control volume around it, and now I have Q dot is going into it. So I have the heat flow going into it, and I have so that Q dot plus m dot air H3 is equal to W dot plus m dot air H4. And again, the work is 0. So I know what the heat flow is. So in this case, I know that I have 25.17 is plus Q is equal to m dot air times H4 minus H3, which is m dot air times C sub P T4 minus T3. And we're going to be able to solve for the mass flow rate of the air, and then we'll look at the volume flow rate as well. So if I do that, so I have m dot A, C sub P for air is 1.0047, and the delta T is 30. And so I have that m dot A is equal to 0.835 kilograms per second. So I have that. So I have that mass flow rate. Now I use the ideal gas law and find the volume flow rate, because fans are rated on volume flow. So we'd want to have the volume flow rate. So if I look at the ideal gas law, PV dot is equal to m dot RT. And I use the inlet conditions. So I have that the volume flow rate is equal to 0.835 times 0.287 times 300 divided by the pressure of atmosphere, 100 kPa, where I get that the volume flow rate is 0.719 cubic meters per second. So with this, I can determine the fan power if I so wish to. So this was a constant pressure process for an open system, and now let's look for a constant temperature process for an open system. So for constant temperature open systems, and again, we're going to restrict ourselves to the ideal gas law. Ideal gas. And we have that Q dot plus m dot E1 is equal to W dot plus m dot E2. H2 minus H1 is equal to C sub P T2 minus T1. And if it's a constant temperature process, this is equal to 0. And so we have then that delta E is equal to 0 if delta KE and delta PE equals 0. So again, I have Q dot is equal to the work, but the work now is a different function. So we remember that the power for an open system is minus m dot, the integral of BDP. And for constant temperature, we can look at the ideal gas law. PV equals RT, or V is equal to RT over P. And what I can do is I can integrate this, so I can substitute this value in here. The temperature is constant, so R is constant, T is constant. And so we have W dot is equal to minus M dot times the integral of VdP. And if I substitute these in, I'll get that the power, and this is equal to a constant, right? So it's all, this term is a constant. And so I have that the power is equal to M dot C times the log of P2 over P1. And C is equal to P1 V1 is equal to RT1. And so I can substitute, if I know the temperature T1, then I would use this value in here. If I knew pressure and volume, I would use that value in here. So it all depends on which one we want to use. So now let's do an example. We will have a compressor that operates at constant temperature, and we'll see what's going on and why this seems to make sense. So if I take a compressor, so I have a fluid going in, it's leaving, we know the temperature is constant, so let's have it have 2 kilograms per second. It'll be air, 300 K, 100 kPa. So this will be the inlet conditions. Now we have a constant temperature process, so we know that the temperature stays constant and the pressure increases. And let's say that we have the pressure here at 600 kPa, and we know that T2 is equal to T1 as we set that up. And I have power going in. I have power going in, and we saw from that the heat is equal to the power that I'm going to have heat going out. So what's happening is the power that goes in, the heat's going to be equal to it. We can find out what the power going in is equal to. So W dot is equal to minus M dot RT1 times the log of P2 over P1. And if I substitute in here, we have minus 2 times 0.287 times 300 times the log of 600 over 100. And if I solve for that, the power is equal to minus 308.5 kilowatts. And this is also equal to the heat. So Q dot. So we see that the power going in is minus because it's going in. The heat leaving is minus because the sign convention associated with heat leaving is a minus, work going in is a minus. So we find both of these. Constant volume makes no sense in an open system because there is no sense as an open system with constant volume. But constant specific volume does make sense. And what this means is that the fluid is incompressible. So if I look at the power term, the work is equal to m dot VdP, and if the specific volume is constant, it comes out, and I have minus m dot V1 actually, times P2 minus P1. And so I can apply this. So for instance, if I had a pump, and I had 2 kilograms per second, I had water, so we'll have H2O, T is equal to 30 degrees C, so V sub F, V1 is equal to V sub F, is equal to 0.001004. And let's have this will be at atmospheric pressure, P1 is 100 kPa, and P2 is equal to 600 kPa. I can then find what the power will be by simply substituting in. So we can see that the power is equal to minus 2 times the specific volume 0.001004 times 600 minus 100. So I have 600 minus 100, and I multiply that out, and we get that the power is equal to 1.0 minus 1.0 kilowatts. So I didn't plan to have it be 1.0 kilowatts, but the numbers turned out to be that way. So for homework, what I'd like you to look at on this section in chapter 6, 6.1, 6.3, 6.5, 6.9, 629, and 641. And I wanted to mention one other type of open system that we've looked at. And it's a throttling process or flow through a valve. So if I look at flow through a valve or a throttling process, I'm going to look at something like this. We have the flow rate, here's the valve, state 1 and state 2. In this case, it's adiabatic, no work is done. And so if I look at the term m dot plus m dot E1 is equal to w dot plus m dot E2, with no heat and no work, I end up with that E1 is equal to E2, and if delta KE and delta PE are 0, so they're 0 for this case, then we have that H1 is equal to H2, and for an ideal gas, T1 is equal to T2.